Okay, this again is in section 7.2. We're still talking about these rotations and so forth. And it's all about the disk method, but now the book in the usual way tries to make it out like all these things are different, but they're really the same, and they talk about the washer method. Well, the idea is that just the difference between whether I'm thinking of a solid disk or a disk with a hole in it. Because, think about if you wanted to make a bowl out of something. My dad used to do a lot of wood turning, and so you could make some sort of bowl, and of course the bowl had to have some kind of thickness, and so it may be that when he turned the bowl, right, you had the outside of the bowl out here, but the inside of the bowl was there, and you could ask, well, how much volume of wood is there in that bowl? Well, they talk about the washer method because the way I would say good problem solving to think about this is, well, find the volume of the bowl without the divot cut out of it, or the inside cut out, and also so find this volume 1, and you would do that with disks, or you could anyway. I'd just come up with all these disks and add that up, and then the inside, that part, you could also cut that up with disks, and there's volume 2, and the volume of wood that's left after turning is just the volume 1 minus volume 2, which were both done with the disk method. Okay, but if you look at, say, a slice up through here, slicing up through there, sure, what you see is you'd see the outside of the bowl and you'd see the inside of the bowl, and you'd say, oh, that looks like a washer. Okay, well, what's the volume of a washer? And let's look at the volumes of these V1 and V2. So V1, as we were doing that, we were taking pi, and we'll call it big R squared, times some h. And this volume 2, we were taking pi times some little r squared times h. Now, when we subtracted those two, V1 minus V2, we got pi big R squared h minus pi little r squared h. And factor out the pi and the h, I got pi h and big R squared minus little r squared. Well, that's their washer method, because it's the same sort of thing here, right? Is, here's little r, there's big R, and to find that area, I could just take pi big R squared minus pi little r squared. And then if I add a thickness of an h, I can multiply that by h and still factor the pi out. But so this is the idea of the washer, but to me, the fundamental idea is, well, yeah, I took two volumes, those two volumes, and I subtracted the smaller one here from the bigger one. And so that's all we're trying to do. And so looking at their example 3, what is this, page 449? what they do is they say find the volume of the solid formed by revolving the region bounded by the graphs of y equals square root of x and y equal x squared about the x-axis. Okay, so there's square root of x. There's x squared. There's 1. There's 1. And what they want to do is send this thing around the x-axis here. But that will do something like make a bowl like this. Right? We have the outside part made from the square root of x and the inside part here made from x squared. And so I'll slice it up. They say rotate around the x. So I slice it up that way. And any given slice, the big R is the square root of x, and the little r in here is x squared. And so I just want to take the difference of those, and so I'll go from 0 to 1. And again, I could do it one of two ways. I could say, oh, this is pi, my r squared minus little r squared dx. And, well, I'll put that here and say that that's 0 to 1 pi square root of x squared minus x squared squared dx. Or, I could do it as the outside one. Okay, so that's the integral from 0 to 1 pi square root of x squared dx minus the inside one. Integral 0 to 1 pi x squared squared dx. And, well, it's the same thing because I can always split up that integral into two integrals at that minus sign. And so either way, we get that same solution. And so what is this? Well, this is integral from 0 to 1 of pi x dx minus the integral from 0 to 1 of pi x to the 4th dx. And actually, we did both of those already. I know that this first one's going to be pi over 2 and the second one's going to be pi over 5. But, well, we'll do the antiderivative, x squared over 2 from 0 to 1, minus our antiderivative pi x to the 5th over 5 from 0 to 1. And so we get pi times a half minus pi times a 5th. And because zeros don't do anything there. And so that's 5/10 minus 2/10 or 3/10. So that's 3 pi over 10. And that is indeed what they got in the text. Now, this is an interesting problem because if I do an example 3 hat, okay, so something like that. Well, I'm going to do the same thing. I'm going to take the square root of x, x squared, that's a 1, that's a 1. But now I'm going to rotate it around the y-axis. So around y-axis. Now I need to get those two radii, right? So I swing it around. Now it's interesting though, because in this case, these were inverses of each other, square root of x and x squared. And so when I change these to y's, right, I had y equals the square root of x. Well, that means x equals y squared. and I had y equals x squared, well, that means x is equal to square root of y, we end up with the same darn problem. So this is interesting that this particular shape, if we think of making a bowl by rotating around the y-axis or making a bowl by rotating around the x-axis, it turns out we get the same thing, because again, we go from as we slice by the y, we go from 0 to 1. So we get that 0 to 1, and then pi, and our big radius was the x squared curve. Oh, okay. So that's the square root of y squared. And our smaller radius was the square root of x curve, so minus, and there's our smaller radius, and that was y squared squared dy, and that is 3 pi over 10. Amazing. Didn't matter which direction we went, we got the same volume. And again, that was just, we had the symmetry of inverse functions going on here. Okay, so that is this idea of the washer method and example 3 and 3 hat.